And welcome, folks. Section 2-4, angles of a triangle. We're not going to read this section at all today. We're just going to dive into it because this is a good one. This is an important one. You're getting one of the most well-known, the most famous theorems in all of geometry. Just by looking at the section title, you might be able to guess what that theorem is. And hey, you know what? In fact, I'll actually ask you guys. Let's see if you get this right. Let's see if you can answer with a fair answer here. My question for you is this as we start this section. What is the sum of the degree measurements in any triangle? Who knows? Anybody knows? Anybody knows? Who can tell me as a fact, right? As a fact, how many degrees do the sum of the angles in any triangle actually add to? Who's going to tell me? Did you tell me? Wait, hold on. Did you in the back? You just yelled it out. You wrote your hand. You're like, I know this. I've known this since 7th grade. It's 180, right? 180, right? Is that right? No, that's not right. That's not right. Okay. The correct answer there is actually the only thing that would have been acceptable for you to say right now isn't anything about the sum of the angles of a triangle. We shouldn't be talking about the sum of the angles of triangles because we haven't even talked about the angles of a triangle yet. In fact, we haven't even talked about what the heck a triangle is yet. So what do you think we need to start today's class with, this section? If we want to talk about the sum of the angle measurements of a triangle, what do you think we need to do next? What do we need to define? That's right, we just need to talk about this guy right here, a triangle. So here we get the geometric definition of a triangle in front of you. Now I know because I have a 2-year-old daughter that starting just after 1 year old or so, she starts to get those picture books and she can spot triangles. I asked, hey, what shape is this? Triangle, right? Got it. Really need to know the definition here. It's just to know what we're working with and also to realize that everything we're going to learn this year comes from those undefined terms. So a triangle is the figure formed by 3 segments joining 3 non-collinear points. So I'm going to show you a triangle is very, very simply. And believe it or not, right, my 2-year-old daughter doesn't know exactly what a triangle is, and I'll explain what that it means in a second. Okay, so a triangle, this is all a triangle is. 3 non-collinear points. So I wanted to point that out. In order to build a triangle, of course, your 1, 2, right, any 2 points will be collinear with one another, but 3 points got to be non-collinear. So when we connect them all together, we see this figure formed, right? This figure formed, which is triangle ABC. And this can be abbreviated by the little triangle symbol ABC here. So this is pronounced triangle ABC. So this is the triangle. You got the 3 non-collinear points. Of course, if you had a third point that's collinear with the other 2, that's just going to be like a line segment when you connect it. That's not going to be a distinct new figure, right? It would just be segment AC if C were collinear with B and A. So any 3 non-collinear points can define a triangle in space. So the reason why this contrasts with my 2-year-old daughter's understanding, and make sure you doesn't contrast with your understanding either, is that the triangle itself is just segments, right? It is segments and the 3 non-collinear points. So these points here, these points here, these points here, and then the endpoints of the segments, that's what the triangle is. So what I'm trying to say is a lot of times, and even in this lecture here, when you prove the very, very famous theorem to do with these angles of a triangle, the interior is going to be shaded in. But is the interior counted as part of the triangle? So right here, this is the interior of the triangle, and then here outside is the exterior of the triangle. Are either of those part of the triangle? No, because a triangle is just segments, and they're formed by those non-collinear points. So the segment includes the endpoints here. If you see a triangle shaded in, like shapes usually are shown to really, really young people, the inside of the triangle is not part of the triangle. The triangle is just those 3 segments here. Okay, so the triangle is 3 segments right here. But as with many different shapes, it gets some sort of special names for the parts of those segments. We could just call these segment AC, segment CB, segment AB, make up the triangle. That's fine. But people will also refer to the endpoints of the segments will be called the vertices, right? This is a vertex of the triangle, a vertex of the triangle and a vertex of the triangle. So the vertices is plural, okay? Vertex, right? Vertex, I would probably all know that. I can move on pretty quickly from there. Vertex, right? Vertex, vertex. So kind of the point that's all by itself at the ends there. And you can see here, triangle ABC, you name a triangle by its vertices. We know we would have a vertex at A, point B, and point C. And later on, those will also identify where the angles are, right? It's the vertex of the 3 angles, right? Each vertex of the 3 angles is a vertex of the triangle. And then we can call the segments that are formed by, right, of course, the angles also get, they're like, this is a side of an angle and this is a side of angle A. So we just call this the side of triangle ABC. So we can see what the sides are based on the way the triangle's named, because we actually see AB next to one another, segment AB. We have BC next to one another. And then what's the third side? The third side is going to be segment AC, right? Segment AC will be, C's got to connect to A, right? So A connects to 2 points, B connects to 2 points, and C connects to 2 points. And that's how you get those three segments. And finally, yes, triangle ABC says that we have an angle A, an angle B, and an angle C. Types of triangles, the definition. So this is an important slide to go over because you probably heard some of this stuff in the past before, and you got to know this language. I go through pretty quickly because I kind of assume you know a lot of it, but I was talking to one of my rock star students from last year who took me for Algebra 1. Great kid and all, but I remember being like, are you nervous about geometry at all? Are you not sure about it? And that person was like, oh, I didn't really do too much geometry in middle school. And I was like, oh, I thought you guys did do stuff in middle school. And she was like, no, not really. And then she said, but I do know what both kinds of triangles are. I do know the two names of triangles. And I hate to say it, right? I hate to be kind of like a mean teacher or whatever, but I laughed a little bit. I did. It's somebody who I consider myself friends with, right? Friends with a friendly teacher-student relationship. But they said they only knew what the two different types of triangles. And to which I responded, hey, there are many more ways than just two ways to name a triangle. So I didn't ask he or she to elaborate on that, but I did say that there are more than two, right? There are definitely more than two names, ways that you can name a particular triangle, okay? The first way, right, you can name a triangle is going to be three ways here. Triangles can be named by their number of congruent sides, okay? So how many sides of a triangle are congruent to another side of the same triangle? Okay, so this first word we have here, definitely write this down, right? You got to know these here. First word here is scalene. Okay, so a scalene triangle, none of the sides are congruent. None of the sides, scalene, right? Scale, get on the scale there, right? If you get on the scale, then you're not in common with any of the other sides. And then we have some other crazy words here. This is a crazy word. This one isn't that crazy though. Here we have isosceles. Isosceles. I think iso kind of means something to do with two. I'm not totally sure, but isosceles. That's an isosceles triangle. You'll just have to remember that word. I'm not going to talk where it comes from, but an isosceles triangle has at least two sides of that triangle would be congruent. So you'd have two sides that were the same length. And it says at least. So if it's at least two sides, it may also be equilateral. This is an important thing to notice here, is that an equilateral triangle has all three sides and have the same length. So equal, right? Equal, and then lateral. Lateral actually kind of means sides. Right? Lateral means usually moving from like side to side, means moving laterally. Lateral means side, and equal obviously means equal. So all three sides are the same. So it's kind of just diagram what this looks like. We've all seen triangles that look like this. Again, the interior is not part of the triangle. It's just the three segments. This is isosceles because we have two sides that are congruent to one another. The third side, not congruent, so we actually call this the base of the isosceles triangle. We'll talk more about isosceles triangles later. Okay, here's another triangle here. These all these sides are 4 centimeters long. So what is the best, right? If I were to say, what is the best name for this triangle, you'd probably say an equilateral triangle because all three sides are congruent. All three sides are congruent. But I would say, what else could you call this, right? Because this actually has another special name to it. Yeah, you could call it isosceles, right? This is also an isosceles triangle. So any equilateral triangle is also isosceles. And this will be important because we'll have theorems to do with isosceles triangles that will also want to be able to quickly apply to equilateral triangles. Okay, so here are examples of those two. And then scalene triangles, right? Most of the proofs we have involving triangles, we usually draw out a scalene triangle because we want kind of a general, nothing special about it type triangle to analyze and prove new facts here. So this is scalene because like we have a shortest side, a medium-sized side, and a longest side. Shortest side, medium side, and longest side here. None of the sides have the same length as one another. So that is scalene. Those are the three there. Okay, so 3 ways to name triangles. Again, that person said just 2. Oh gosh. There are several more I'm going to give you here because you can also define triangles by the type of angles that they have here. Okay, so you could have an acute triangle, you can have an obtuse triangle, you can have a right triangle, and you can have an equiangular triangle. Equiangular triangle. So make sure you write all these down and think about them, because we'll be talking about it the next several days here. Okay, acute triangles, that's pretty easy to know, right? Acute, we know what an acute angle is. Like these would be an example. These would all be examples of acute triangles. Every one of these angles here is less than 90 degrees, right? Less than 90 degrees. If it's less than 90 degrees, it fits the definition of an acute angle. So if we have 3 acute angles, and remember, angles add up to, we'll get to that theorem later about what the angle measurements of a triangle add up to. But most triangles you see actually will be acute triangles. Then we have obtuse triangle. Okay, so the definition of an obtuse triangle is a triangle with an obtuse angle in it. It doesn't actually say how many obtuse angles there are. That'll be something that we'll get to later when we actually prove a theorem. But if it has an obtuse angle in it, then we can call it an obtuse triangle. So picture it, right? It looks like something like this, right? A point here, a point here, and a point here would form an obtuse triangle, because this would be an obtuse angle right here, right? This is an obtuse triangle. So you can sketch it out like that. A right triangle, right triangle is, you got a right angle. I think you guys know that. You might know a theorem, a very famous theorem involving right triangles. Okay, this is obtuse. I'm trying to show before. Obtuse, and this is right. This is right. It's right there. And then equiangular, all angles congruent. Try to picture what that looks like, right? All angles congruent. So you got to start with something like this, that, kind of. Those angles look kind of the same. So actually, hey, see what you notice with this one. Equilateral triangle and equiangular, right? Just to observe that for a second. And then think if we can prove something there maybe a little bit later on. Okay, those are the names for triangles. Hey, you got this kind of a triangle, you got to know, right? You're either talking about what types of angles are in them. Acute, all 3 acute angles. Obtuse, one obtuse angle, right? One right angle, and equiangular. All of them are the same measurements, right? Same measurements, right? They're all congruent to one another. So if you said, hey, an equiangular triangle, this is what you're given. You're given that angle, congruent to that angle, congruent to that angle. And you also got to know scalene, isosceles, and equilateral. Okay, so please know those, study those. Those will come up on the homework problem sets as well. All right, so here's the big one here. This is the thing, the main thing of today's class. And then we actually have another second very famous theorem later in class today. This will be our long lecture, I think, kind of the week. But here's our theorem, starting out here. You might know the answer. Theorem, the sum of the measures of the angles of a triangle, of any triangle, right? I should have said any triangle. The sum of the measures of the angles of a triangle is what? Who's going to tell me? Who's learned this before? Who's like, Mr. Fortin, I've done problems like this before. What is it? All right, fine. You just tell me. Is it this? 180. A hundo and 80, my friends. 180. I think I remember making this slide last year, and I was like, this is the point in the year where my class really goes crazy. It goes nuts, right? It goes nuts. Look at this. Let's watch that again. It's just like, hey, why do this if you can't have fun? Come on. This is sweet. All right, so stuff's getting crazy. We're doing ridiculous stuff. Whatever. We still got to prove this, don't we? We got to prove this. So a lot of people say, like, a lot of people remember this, actually. I talked to them, and they're like, hey, how many degrees is the measured an angle in a triangle? How much is it? And it's like 180. They'll say 180. And I ask, how do you know that? Or how do you remember that? And they'll say, oh, well, I learned it in middle school. And, the angles of a triangle, right? They make a straight line. And I'm like, oh, what do you mean by that? So when they say that, I kind of think that probably this is perhaps how you learned this fact in middle school, or you learned this rule in middle school, was that perhaps you just compared the angles here by doing this. You took angle number 1 and angle number 2, you placed them next to each other so they were adjacent to one another all of a sudden. And finally, you took angle number 3 and you did it right here. Okay, so just I wanted to point this out to you because you've never seen that before. Because if you take all 3 angles of any triangle, right, and say if we cut them all out and twisted them around and placed them next to one another, it's easy to see this is 180 degrees. Look, because angle 1, right, this angle here, right, this thing here would be a straight angle, right? It would this side of angle 1 and this side of angle 3 would form a straight line if we had angle 2 wedged in between there. Okay, so we can clearly see this, clearly observe that the 3 angles add to 180. So are we done here? Is this a theorem, right? Is that a theorem, or right? If we're just using this as a rule, would it remain a rule and therefore be a postulate? No, this is a theorem. We can actually prove this one, which means that what are we going to do right now? We're going to write a proof. Time to do it. Time to do it. So let's go do that right now. And this is a good proof. I like this proof because it'll include one of the things that I said you needed from section 2.2 last class. Anyways, given here. Okay, so we're going to prove this, and we want to prove this for any triangle. So given, okay, the sum of the measure of the angles of a triangle is 180. So maybe you're given the angles, but every triangle has 3 angles. So in this one here, you're actually just given the triangle, right? So given a triangle. Okay, if you have a triangle, then what can you say? Right? Well, in triangle ABC, sure, you're given the angles. What are the angles you're given? You're given angle A, angle B, and angle C. So what are you going to try to prove about angle A, angle B, and angle C? That their measurements add to 180. Okay, so this is the proof we're going to do right now, and this will prove our fact. Right? Remember, this diagram is just like a generic scalene triangle right here. Nothing special about it, but we're going to prove this fact. For any random triangle, we can prove that their angles actually always add to 180. And therefore, we can use this as a fact going forward for the rest of the year, and know for sure it's a fact. Okay. Statement number 1. Here's where the good stuff comes in. Okay, so you're trying to prove this one. It says given triangle ABC. So I'm not going to say, hey, what's the first step here? Because it's always the first step. You're not going to write the given because we just learned what a triangle was like 10 minutes ago, or at least what the geometric definition of a triangle was. So we don't have anything we can do with triangles aside from say, here's the definition, right? It's 3 segments formed by 3 noncollinear points. That doesn't help us in a proof at all. So there's no reason to say triangle ABC and given, okay? So in this problem here, we can maybe think about how we can get 180 written down. Not really want any way we can get 180 written down into the proof. We can maybe talk about adding measure of angle 1 and measure of angle 2, but those aren't adjacent to one another. So there's no way we can add angles because angle addition postulate is just talking about adjacent angles. So the third thing here, and one thing that'll start coming up, and you don't have to get this right away, but you'll see it. It'll be a pattern that comes in here. The first step here is to actually draw in a line to the diagram. Draw in a line to the diagram. Where am I going with this here? What's something we learned recently that we can draw a particular line into a diagram that might help us with the proof? Well, let's put statement number 1 down and we can maybe think of it. Here's the statement. Through B, draw line BD parallel to AC. Okay, parallel to AC. So it says here that what I'm going to do first, because I want to use angle addition postulate so we can start talking about adding angles, and I also want to talk about 180. So I'm probably, that's an angle addition postulate. It's a way to get the number 180 into a proof, because if you're adding 2 adjacent angles that form a straight angle, it would get 180 into a proof. So anyways, it says through B, draw BD, line BD parallel to AC. So this here, draw that line in, you might see what theorem it is that allows us to justify this. Okay, so I drew in, and if you weren't looking at the top right, please look at the top right of the screen. I'm drawing in line through B that's parallel to AC. And I'm just calling it line BD because we didn't have a point named D yet. So you're allowed to name a point there, okay? What was the justification of that? How do I know I can draw through a point? Not on this AC, I can draw a line parallel to AC. And that's this one right here, okay? Through a point outside the line, exactly one parallel line can be drawn. And we drew that one and only, right? Our unique and exists line, our unique line that does exist. We drew it through point B parallel to AC, and we're good to go here. So guys, this is an important one because a lot of your theorems rely on being able to draw this parallel line in. Helps us prove a lot of things, or at least helps us prove this, which gets us to proving a lot of more stuff. And this is very, very famous in the history of geometry because this is a theorem in your textbook. But remember, I told you this is the most famous of Euclid's postulates. And if you're going to really be studying this stuff in the future, you'll want to know which postulate this is. What number postulate? Who remembers from last class? This is Euclid's 5th postulate. Yes, 5th, 5 of 5, because he had 5 postulates. And this is his most famous one, otherwise known as the parallel postulate, of course. Parallel, Euclid's parallel postulate, Euclid's 5th postulate. Anyway, how did that help us? We now have parallel lines. When you have parallel lines, what are some things you can say? Okay, what are some things now you can say? So you can always try when you're writing proof stuff, you can try putting in a parallel line, and then you can make observations. Well, if you have parallel lines, ooh, look, there's a transversal right here and another transversal here. So it looks like you can actually say angle DBA is congruent to what? Angle BAC, okay? Angle BAC. So we'll get to that later. I'm maybe going to number the angles now. You're always welcome to number. So if you're on a test and you don't want to mention the angle DBA, you just want to call it angle 4, then just write a 4 down there. Make it angle 4. So angle 4 is congruent to angle 1. And angle 5 is congruent to angle 3 because these are alternate interior angles. And if you have parallel lines cut by transversals, then alternate interior angles are congruent, okay? That's helpful. But maybe where I wrote this proof is I wanted to get 180. Look here, you always work forward in a proof, and working forward would be like saying alternate interior angles are congruent. The other way to do it is to work backwards. Working backward in a proof is looking to something that we need to say and figure out what's something that allows us to say that angles added together equals 180. And that's the angle addition postulate. Okay, so we're going to start with the angle addition postulate. And the problem with the top here, so I know that angle 4, angle 2, and angle 5, right, obviously common sense, these would have to add to 180 because this is just a straight line up here. Right, and this would, if we had a point at B here, DBZ would be a straight angle. The problem with that is that the angle addition postulate is written for 2 adjacent angles that form a larger angle. Remember, angle addition postulate is part plus part, right? Part plus part equals whole, right? So measure of angle 4 plus measure of angle 2 equals measure of angle DBC would be angle addition postulate. Angle addition postulate isn't written for adding 3 angles together. It's only written for adding 2. So it's not part plus part plus part equals whole. Okay, so that's going to make this theorem appear a little bit funkier than I think it really needs to be. If we, really should just have written angle addition postulate differently to avoid this. But anyways, look at what I wrote here. Measure of angle 5 plus measure of angle DBC. Okay, so part plus part, okay, equals whole. And this would be a straight angle right here, right? DBZ, right? 5 plus DBC measures this whole 180 degrees, spans this whole 180 degrees. Okay, so part plus part equals whole. Okay, ultimately my goal is I want to say measure of angle 2 plus measure of angle 4 plus measure of angle 5 equals 180. And then I think what's going to happen later. We're going to basically use substitution to get us to the answer. But anyways, I'm going to ahead of myself. So also I lumped this into one step because this is angle addition postulate. What have I written down here? Well, I didn't want to talk about just about measure of angle DBC because I wanted to talk about 4 and 2. So if we add measure of angle 4 plus measure of angle 2, then that would equal measure of angle DBC. So this is just angle addition postulate used twice. And I put this in, I highlighted this in red just to emphasize to you, angle addition postulate, it's fine if you want to do part plus part equals whole, or you can write whole equals part plus part. That's fine. That's fine too. Another thing you'll see the book do is that they'll actually do the whole angle minus one of the parts equals one of the other parts, and equals the other part. And that would also be okay for using angle addition postulate as your reasoning for that, if you want to do it that way. Okay, but you can't add three angles together to be the whole angle. That doesn't work for angle addition postulate. So here's what you have to do. You have to use angle addition postulate here, and then to get from step 2 to step 3. So now I want to say measure of angle 5 plus measure of angle 4 plus measure of angle 2 equals 180. And the reason why I can do that is because I have measure of angle DBC here as part of this expression, and I know that that part equals measure of angle 4 plus measure of angle 2. So if I'm going to take this and put that into this equation up here, it's going to become statement 3. So what's the reason for that one there? It's not transitive. It's what? It's substitution. Okay, so I substitute something that measure angle DBC equaled into as a part of an equation, not just like the whole expression on one side. That's what the difference between substitution and transitive. All right, we're almost there. So I kind of made the other observations to get us to finishing this proof earlier on, but we haven't written them out, right? We'd have to write them out if we wanted to fully prove this thing in here. Okay, somebody tell me real quick. Right, alternate interior angles. I got it, okay? So measure of angle 4 equals measure of angle 1, and measure of angle 5 equals measure of angle 3. And this is going to help us. We're going to use substitution again at the end here, okay? Let's just write it down again. If 2 parallel lines are cut by a transversal, then alternate interior angles are congruent. Okay, so we basically in step 3 have said what we wanted to say to prove things here, except we've done it with measure of angle 4 and measure of angle 2 in there. We don't want that. We want measure of angle 1 and measure of angle 3 we haven't talked about. Measure of angle 3 we haven't talked about yet. We just, measure of angle 2 is okay, but we want to get rid of 4 and 5 and replace 4 and 5 with what they're equal to. 4 is equal to 1 and 5 is equal to 3. And finally, we can wrap this up by doing substitution, going from step 4, substituting what 4 and 5 equal into step number 3, and then we're good to go. We have our statement here. We have the fact that those original 3 angles that made up the triangle do in fact have to add to 180 because it follows from all the stuff that we've been proving all along. And so we'll take it as theorem. The sum of the measures of any of the angles, of the angles of any triangle is 180. Okay, and you might be thinking, is this the only way I could have proven this? Meaning drawing the parallel through B parallel to AC. No, if I had done this through point A, for instance, if I had drawn a parallel, I would just have to draw the parallel to BC through point A, and I would have been able to prove it the same way, right? This angle plus this angle plus this angle, eventually I'd prove that would have to equal 180. This angle would equal angle 2, and this angle here would equal angle 3 because it would be alternate interior angles. And through this, by the same logic, I'd be able to arrive at my answer here. So even though it's presented to you in the book and also in our proof like this with the parallel up here, this is just for a generic triangle, right? A generic triangle, and we know that all triangles now, their angle measurements would add to 180. All right. Huge proof there. And another just quick aside to point out, because we did actually use that thing that I spent most of last class talking about, which is Euclid's 5th postulate, the parallel postulate, right? Through a point outside a line, exactly one parallel can be drawn. Do you guys remember why that was so famous or how it became so famous? So remember, mathematicians over the past 200 years have basically started ignoring this, right? This theorem in our book, or Euclid's postulate, just to see what happens, right? To see what other geometries might emerge if you can't do this, right? If we don't have this idea that through a point outside line, exactly one parallel can be drawn. So just one other quick side note about this, about some of these non-Euclidean geometries, right? Non-Euclidean geometries are geometries that got formed because they ignored this fact. They ignored Euclid's 5th postulate here, the parallel postulate. So those geometries I told you a little bit about, another key distinct thing about them from the geometries you're learning this year is that the sum of the angles of a triangles can be less than or greater than 180 degrees. So in our Euclidean geometry, the type of geometry you're learning this year, these angles will always add to 180, right? The angles of a triangle add to 180, the measurements add to 180. But for instance, in hyperbolic geometry, hyperbolas will be something you'll study in Algebra 2, but maybe I'll talk a little bit about the end of the year. Anyways, this is that one where your planes are kind of more like a saddle, right? Like a saddle of a horse, right? Saddle, so it's like a saddled hyperbolic plane here. And this was an example of 2 parallel lines. So remember, if these are parallel lines, right, because they're coplanar and they don't intersect, through like this point right here, through this point, which this line goes through, right, there'd be another curved line. There'd probably be several curved lines that would go through a point not on this line that would also be parallel to this line here, okay? So this hyperbolic geometry ignores this, and one of the consequences of this is that you end up, because of the curvature of the plane, you end up getting several triangles you can make that, say, for instance, meet at these 3 points. First of all, these wouldn't be the only triangles that would meet at these 3 points here, but if you look at this, do these look like they add up to 180 degrees? Well, do these look pretty acute? These are very acute right here. So in hyperbolic geometry, the triangle angle sum is actually less than 180. So and somebody asks you how many degrees are in a triangle, you got to ask, well, what kind of a plane are we talking about here? Are we talking about a hyperbolic geometry plane? Or are we talking a Euclidean geometry plane? Because in Euclidean geometry, it's 180 degrees. Here, triangle angle sum is less than 180 degrees. And of course, based on curvature, right, you could have another triangle that goes here, which is even more acute than this. Another one here is spherical geometry. That was the other one we looked at. Like Einstein really followed spherical geometry. And let's look really closely here. If you're on a phone, it might be hard to see this here, but this is a triangle defined on a sphere. So of course the Earth is spherical. So if you're studying the surface of the globe of Mother Earth, then you're doing spherical geometry. And here's how you would define a triangle in spherical geometry. So remember, a line in spherical geometry is defined as the largest circle you can draw on the plane, right? On the plane itself. The largest circle, so it would be, for instance, going from the equator here all the way to the North Pole and back around to the South Pole would be an example of a line drawn, right? So line, right? Start with a point here, draw it towards the North Pole, and then just keep drawing would eventually go to the South Pole and back. So the thing is that if you did this here around, looks like India, and then equator just below India here, and then you did it around the equator, I don't know, where's that, Australia or so, and you drew straight up, right? You draw another line right here. First of all, this is an equator here. You'd actually form two 90-degree angles. Look at this here. If you go straight up from the equator in one place and straight up from the equator in another place, and you're using the equator as your other line, because the equator would be a line in spherical geometry, right? This would be the largest, equator is the largest circle you can define on a sphere or on the Earth. These are two 90-degree angles. But these two 90-degree angles aren't parallel to one another. So on the plane, if your plane is a globe and you have transversal across two lines that are perpendicular to both lines, these lines are not parallel, right? They're eventually going to meet. And where are they going to meet? They meet in the North Pole. Okay, so here, a triangle here is formed even though you already have two 90-degree angles. So this is 180 degrees, and then this is 50 degrees. So spherical geometry, the triangle angle sum is more than 180 degrees. More than 180 degrees. You might be thinking, well, I've had a globe before, right? So what about a map, right? If we take this and we put this on a map, this is actually what the same triangle would look like on a map, although this isn't India or the ocean looks like here. It's just looking like they're trying to show it to you a little differently. So if you drew a triangle on a map, it would be, yes, it would be 180 degrees. Why? A map is what? Map is two dimensions. So this would be going straight up. Pretend the North Pole is like right here, right? If the North Pole is right here, this would be drawing straight upward, right? So due north is the North Pole. Due north is the North Pole. And even though on a globe, it looks like a 90-degree angle, on a map, this would look like a 50-degree angle. If this is the equator or parallel to the equator. Okay, so just it depends, right? The way you're defining things and the way that your planes are perceived is going to change some of the conclusions you'll make. Okie dokie, back to our Euclidean geometry. So that was a lot to think about and not necessarily stuff you'll need to be responsible for now. You'll be responsible for stuff like this. And this is pretty easy right here. So we're going to go easy again for a couple minutes. And then I got another really important theorem towards the end of this lecture today that I'll hopefully get to in about 5 minutes or so. Oral practice, back to our Euclidean geometry, okay? So this is a triangle on our normal flat surface plane, so we don't have to worry about weird planes or non-Euclidean geometry. Measure of angle C, what does it have to equal, okay? Well, this is 80, that's 60. What's this one going to have to be? 40 degrees. Hopefully you guys got that. All right, we can make that conclusion now. What does A plus B plus C equal? 180. Well, if this is 60 and that's 80, then we can maybe say this is x right here. We're solving for x. So let's take 180 minus 60 minus 80, and that's going to equal x, right? That's going to equal x. Or you can think about it as x plus 60 plus 80 equals 180. And I'm all confident you can solve a problem like this. 80s cancel, so we're left with x plus 60 equals 100. And subtract 40 from both sides, x equals 40. And we're good to go. These should be a very easy problem for you guys, even as ninth graders, right? Even in Algebra 1. All right, definitions. Some more definitions here because I said I had another important theorem coming up, and I was hoping to get to it within 5 minutes. Your next important theorem is going to have to do with exterior angles. Yes, the exterior angle theorem. That's an important theorem that you'll have to know. So don't forget it already. Exterior angles are this, and exterior angle theorem's coming up. And let's write this definition down so you know what we're talking about here. So first of all, if we're talking about the angles of a triangle or an angle of any other figure, you're talking about interior angles formed by that figure, okay, formed by that figure. So the triangle itself, remember a triangle is just three non-collinear points, right? And then you join three segments, 1, 2, and 3. So The angles of a triangle are just going to be where this segment and this segment form an angle right here, where this segment and this segment form an angle right here, and where this segment and this segment form an angle right here. 3 interior angles are the angles of a triangle. There's another thing that we do talk about, though, because there are conclusions, then they're going to help us with some future proofs. So this will come up in future proofs too, and it's a helpful observation to make to save time too. And that's if you talk about the exterior angles that a triangle can form. So an exterior angle is an angle not just of triangles, but it's an angle that's formed when you extend a side of a figure. Okay, or when you extend a side of a triangle, because we're just talking about triangles this chapter. So if I have my triangle right here and I get all my line segments and I extend all of the lines, right, extends this line here, extends this line here, and extends this line here, and maybe I actually extend that line too, and I extend that line and this line, exterior angles get formed, okay? So this is an example of if we just extended one of the sides in one direction, right, left this as a ray, we're just showing one exterior angle. If we extend this one, we'd have another exterior angle right here. And I'll show the difference between exterior angles and vertical angles can get lost in the fold here, and I'll discuss that later. Okie dokie. The important thing is when you're thinking about this exterior angle, maybe you're highlighting this exterior angle here because it relates to some of these angles of the triangle. First of all, an exterior angle, how is an exterior angle related to its angle that it's adjacent to? Well, by the angle addition postulate, what must this angle measurement plus this angle measurement equal? 180 degrees. Oh, very interesting. Okay, so exterior angles are related to this angle, but they're also related to these two angles here. Okay, so this is the adjacent interior angle, and it is supplementary to the exterior angle. Okay, so exterior angles, the angle formed by when one side of a triangle is extended, and it is supplementary to its adjacent interior angle. Another thing to talk about, so this is its adjacent interior angle, so then you might be thinking, what are the other two angles referred to as? Well, they're the other interior angles, so interior angles is written here, but these are called the remote interior angles. To be kind of remote from something, I'm calling in, be dialing in remotely to our meeting or to our Zoom call. So you guys should know the feeling of being remote from school means you're away, right? Means you're away. You're not in that same place, okay? So remote, these are the two remote interior angles, right? They're remote from this exterior angle. So write that down here, and we got remote interior angles, okay? So exterior angle plus the adjacent interior angle equals 180 degrees. I'm going to ask you guys, what can we deduce about these two remote interior angles? Is there something that we can maybe say about these remote interior angles? Well, this plus this equals 180. Hint, what is this plus this equal? Also 180. Okay, let's get into it. Let's get into this theorem right here, and let's go ahead and write the theorem down. So this is a very important theorem. This is called the exterior angle theorem. That's right, friends, the exterior angle theorem, otherwise known as the EAT. Okay, I'm going to abbreviate that down there. I wish I actually wrote that down there myself, but theorem, the exterior angle theorem, EAT. And if I said EAT, right, and I spelled EAT, what word does EAT spell? That's right, the eat. So a lot of times you can call this theorem the eat. That's fine. Called the eat. All right, we got our eat. We got to figure out what the eat is here. Theorem, the exterior angle theorem. And that is that the measure of the exterior angle, so this exterior angle right here of a triangle equals the sum of the measures of its two remote interior angles, right? Two remote interior angles. And the logic of this, if you haven't worked through it yet, we're going to work through together. But basically, exterior angle plus this angle equals 180. But then again, this angle plus these two things also equal 180. So if we subtract this from 180, we get the sum of these. And if we subtract this from 180, we get the measure of this one. So therefore, the sum of this and this need to equal the same thing. And this just helps us with some algebra problems that we'll have in the short term, but proving stuff in the future. Okay, so the proof for this, I think you guys will be able to prove this just fine, is left for question number 21 in tonight's homework. For now, try using the EAT to solve for x in the diagram on right. Okay, so just a quick algebra problem involving this. In case you've dozed off, you got some algebra, something to solve here. Ready, set, go, solve for x. You got this. I'll give you 45 seconds. Work it out, work it out. For that x. What is this 3x's relationship with that? what are these guys' relationships with that? So therefore, what are these guys having related? 10 seconds. 5 seconds. 4, 3, 2, and 1, and we're done. You're done. Okay. Hey, one thing is that if you understood the exterior angle theorem, then this is a very quick one to kind of get. But again, right, exterior angle theorem is that exterior angle of 3x degrees, it has to equal the sum of the remote interior angles. So that's x plus 80. And very quickly, you'll be able to determine, right, if we subtract x from both sides to cancel out that x, and then we're left with 2x equals 80. So very quickly, we'll be able to determine that x would have to equal 40, because we divide both sides by 2 here, and x would equal 40. But I showed it a little bit differently in case you're still struggling with, well, what is this exterior angle thing? I marked this as y degrees right here. Okay, if this were y degrees right here, I'm just going to look at it and doing it with a little bit more work, just to maybe have it jump out to you. This term jumped out to you a little bit more. So here, what do we know about 3x plus y? Okay, 3x plus y. Well, 3x plus y has to equal 180. Okay, right, has to equal 180. What's another thing that has to equal 180? Well, these three angles right here, right, also have to equal 180. So x plus 80 plus y also equals 180. Okay, also equals 180. So we have a theorem to save us time, so we can start with it like this here, but you probably wouldn't be able to solve this on your own, even without this theorem here, okay, because it would just take taking more steps here, because what we notice here is that there are two ways to get 180. These are supplemental, and then these add to 180 degrees. And then we'd be able to combine, like equal values method or transitive property, right? Get it that you'd have 3x plus y equaled x plus 80 plus y. And I got a plus y on both sides, so I can knock those out. And look at it here. I got 3x equals x plus 80. So I just wanted to point that out to you, right? This shouldn't look like a completely crazy theorem to you, because it's very easily to prove using algebra. And we'll look at it one more time in a second, but I just wanted to point out another important thing about exterior angles and how many exterior angles do get formed if you extend all the sides, right? All the sides in both directions here, okay? So it's a special note here. Note if we extended the 3 sides of any triangle in both directions, right? So 3 sides, 2 directions, that's 6 total directions we're extending the triangle. So that means we end up with 6 exterior angles. And so let's get a look at this here. Let's not read this fact here. That'll just be for you to look at in case you're studying later. But basically, right, if we extended this side here, right, both ways, it would form an exterior angle here, 4 and 2 right here, right? 4 and 2, 4 and 2. So 4 would be equal to this angle plus this angle, and 2 would be equal to this angle plus this angle. We extend this line, it would form 3 and 5. We extend this line, it would form 1 and 6. Okay, so the angle that gets formed obviously is going to be, you're not going to include the side, this angle that gets formed isn't the side of the triangle isn't going to be from where the side got extended, meaning I extend this side, and this angle is made up of the extension of this side and the one of the other sides of the triangle. That's where exterior angle 6 comes from here. Okay, so you might be thinking, well, now at this vertex I have an interior angle, I have 2 exterior angles. What's the deal with this angle right here? Why are these not exterior angles? Because they're located, this angle, and this angle are technically located in the exterior of the triangle. They're not interior angles. They're not exterior angles. Why aren't they exterior angles? What will we refer to these as? Well, these here are just vertical angles to the interior angles. So there's nothing special here. You're not including this in the exterior angle theorem, because this here would just equal this angle right here. And this here would equal that angle. And this here would equal that angle. So these are what we would just call vertical angles of the triangle. Okay, so by exterior angles, you're talking here, here, and 6 get formed by extending both sides in both directions. Summary, let's look at this one more time, exterior angle theorem. So our exterior angle theorem here is for our exterior angle here is W, right? We extended line BC, okay, extended line BC. So we'll use BA as a side of the exterior angle, and we'll use the ray that got formed when we made ray CB, right? Starting from B in this direction. So this is W right here. So W plus X, what does it equal? 180. What's another thing that equals 180? Well, X plus Y plus Z equals 180 because of the big theorem, the sum of the measures of the angles of a triangle, any triangle in Euclidean geometry, add to 180. Okay, so we got 180 right there. Next step, how can we solve for, what are we solving for here? Oh yeah, we're just trying to show that W equals Y plus Z. How are we going to do that? How we do that algebraically here? Transitive property right there. That's right. W plus X equaled 180. And Y plus Z plus X equals 180. So this sort of skipped over a step right here, but what I probably would have said between is that, right, transitive property, W plus X equals Y plus Z plus X. Two things that both equal the same thing must equal each other. So we bring that over there. And then again, because I have plus X here, I can subtract X from both sides. And then I have proven more algebraically this time that the exterior angle theorem is accurate, that an exterior angle is equal to the sum of its remote interior angles, okay? And that's written out for you again here. Some other quick questions that I have about the exterior angle theorem. Well, with this formula, right, W equals Y plus Z, would it still work for this guy right here, right? Would it still work for this guy? And here I got Y and Z over there, so those are the remote interior angles. Yes, it totally would, right? Totally would. Equals 180, equals 180, and then transitive property and subtracting X from both sides, boom, same thing. Same thing here, right? This angle here. So notice here that this exterior angle and this exterior angle, oops, if I knew that the exterior angle's measurement is Y plus Z, do I need the exterior angle theorem to then know that this angle's measurement is Y plus Z? No, not necessarily, because this angle and this angle and this angle, they're vertical angles, right? Vertical angles. So at exterior angles, even though there are 6 of them, there's only going to be 3 unique measurements, because each pair, right, the pairs of exterior angles at a vertex are going to have the same measurements. Okay, so let's practice here. A little more exterior angle practice. X, somebody tell me X. What's X going to be? Well, here are 2 ways to do it, right? This is 125 degrees. That's the easiest way to do it. Just add them together. It's super easy. Are you kidding me? Waited this long for something this easy? A little bit harder. A little more algebra here. Take 15 seconds. See if you can figure this one out. 20 seconds. 30 seconds. Race, set, go. What's X going to be? Well, this is an exterior. These are all interior angles. What do they all add to? Ready, set, go. You guys got this. Who's going to tell me first? Boom. Right, we got to add them all together. 4x plus 3 plus 2x plus 1 plus 2x. They all equal 180. Combine like terms, and it follows. So hopefully you got 22 here. 6x, 8x, okay, 8x, and then we have 4 1s. Subtract 4 from both sides, divide both sides by 8. X equals 22. There we go. Finally, last question here. Practice, find x, y, and z. Tell me 2 ways to find y and z. So, x, y, and z. Well, x is easy, right? Only one way to get x, and x is going to be, this is 110, so what does x have to be? Well, they all add to 180. Subtract 80, brings us down to 100, subtract 30, that's 70, okay? So it's easy to get that with 70, be 70 degrees here. So that's going to give you an easy way to get y, okay, an easy way to get y, but what's another way to get y? Okay, so y is obviously supplemental to this, so y has to be, 110. Okay, what's another way to get y? Oh, y is also an exterior angle, so the remote interior angles would add to get to be y, and yes, this is a good way to double check your answer. 80 plus 30 does equal. Okay, we're good to go. Okay, what about z? So there's 2 ways to get z right here. So this for 110 plus 20 is 130. Z would have to be 50. Okay, but why did I already know that z had to be 50 actually before getting? This angle addition postulate, this is 50 degrees. And then that's 80 degrees, so 50 plus 80 is 130. That means z has to be 50 as well, because 180 minus 80 is 100, minus 50, minus to 50, z would be 50. And those are answers. Okie dokie, there is your homework here. This is day 1 of 2, so day 2 will still be a decent sized lecture, but it'll be significantly shorter than this one. So I think that you'll get up and running tonight, and you'll ask any questions when we do one another. But big things again, how we got how we proved the sum of the measure of the angles of a triangle is 180. Really, how we proved that is the important thing, and then also knowing the exterior angle theorem, which you will prove to. So, problem number 20. I'll do that later. All right, take care, guys. Have a great day. Bye.